This lesson's on applications of circular motion. Let's start by talking about vertical circles. Imagine that we have a ball on a string. We're looking at it from the side here, and it's being rotated in a vertical circle. And we're asked to decide what forces are making up the centripetal force at the top and at the bottom of the circle, and also where the tension is the greatest. So let's step back for a moment and think about our familiar F net is equal to ma type problems. Typically what we've had to do is find F net from the free body diagram, identify the forces, and sum them using directions as appropriate to find F net, and then use that often to solve for something like acceleration. Well, in centripetal motion problems, we're doing the same kind of thing. We're finding the net force in the in direction, or pointed towards the center of the circle, and that's going to be equal to the mass times the centripetal acceleration, which is v squared over r. So we're going to follow the same kind of procedure as we have in non-circular motion type questions. We just need to recognize that this is now our F net pointing towards the center of the circle, and this is mass times acceleration. So at all points on the circle, the weight is acting downwards on the mass, the weight or the force of gravity, and that's equal to mg. And that's going to be equal all throughout. The weight's not going to change. The force of tension, however, is going to be pointing sometimes in the same direction as the weight and sometimes in the opposite direction. At the bottom, it's going to be pointing opposite to the weight, inwards towards the center of the circle, and at the top, it will be pointing in the same direction as the weight, downwards towards the center of the circle. So our centripetal force is equal to the sum of all of the forces along the radius pointing in towards the center of the circle. So we use in towards the center of the circle as our positive direction. So the centripetal force at the top is going to be equal to the force of tension plus the weight, whereas the centripetal force at the bottom is going to be equal to the force of tension minus the weight. And so we can see that the force of tension at the bottom must be bigger than it is at the top, because at the bottom it's the difference between the force of tension and the weight pointing inwards that's giving us our centripetal force, whereas at the top the two sum together. And so the force of tension has to be larger at the bottom to not only counteract the weight, but whatever's left of it when this difference is done, that's providing the centripetal force to keep the object going around in a circle. Let's take that a little further. We could be asked to find the minimum speed the ball must have at the top in order to successfully continue in a circle. Well, at the top we found that the centripetal force is equal to the sum of the force of tension plus the weight, because they're both pointing inwards. And we also know that the centripetal force must be equal to the mass times the linear speed squared divided by the radius. Well, if we want v to be as small as possible, that means that we need the centripetal force to be as small as possible. If this side decreases, then this side must decrease as well. If we want the centripetal force to be as small as possible, there's only one thing on the right side of this equation that can change. The weight is fixed, so we need the tension to be as small as possible. What's the smallest tension we could have? Well, we could have a tension of 0. So in this case, the tension is 0 at the top, and the string is just slackening as the ball negotiates the top of that circle. So let's set these equal to each other. We have a tension of 0. Tension of 0 plus the weight is equal to our centripetal force, and so masses cancel, and solving for v, we get v is equal to the square root of g, the acceleration due to gravity, times r, the radius. That's the minimum speed the ball must have at the top, where we'd have 0 tension and it would just continue to negotiate that circle. Let's turn this around a bit and think about a car traveling with constant speed over a hill with radius of curvature r. So here's my hill, and now I've got a car traveling over it. And the centripetal force in this case is given by the weight minus the normal force. The normal force is going to be pointing upwards. And so my centripetal force is equal to the weight minus the normal force. And again, the centripetal force is equal to mv squared over r. So as I increase the speed, as v goes up, the left side of the equation goes up, so the right side of the equation must go up as well. Well, how is the right side of the equation going to go up? only if this goes down. So as v picks up, as we go faster and faster, the weight can't change, and so the only way the right side of this equation is going down is that the normal force is going down. That'll be experienced by the riders as feeling like their weight is decreasing, because the sensation of weight you get is from the normal force pressing on you. At the point where the normal force is 0, they'll feel momentarily weightless, and if they start speeding up even further, then they won't be able to negotiate this hill, and they'll actually come off the ground. They'll be traveling on a curve of bigger r. You've probably experienced this sensation of weightlessness yourself if you've gone on a roller coaster where they have those little bumps after the big hill. You pick up speed on the big hill, and then you feel weightless as you go over these little bumps because of this effect. Let's now look at bank turns. If you've watched cycling on indoor tracks or velodromes, you've seen that the tracks are banked. Let's call that the angle of inclination theta. So why is that? Well, that allows the cyclists to recruit part of the normal force to act as part of their centripetal force. Here's my cyclist going around a curve on a curved track. The normal force is acting perpendicular to the surface, their weight is acting downwards. First, let's think about where the circle is that they're tracing. We're looking at them end on, and they're going around at this altitude all the way around the track. So in fact, the center of the circle is over here. It's a common mistake to think that it's at the bottom of the track or that it's somewhere down here, but if they're maintaining this height, they're tracing out a circle like this at this height. So the center of the circle is over here. Remember that we always want to draw our axes so that the direction of acceleration runs along one of the axes. That means in this case, because the centripetal acceleration is pointing towards the center of the circle, we want our axes like this. And now I can resolve the force, the normal force, in these two directions. I can find the normal force in this direction and the normal force in that direction, or the components in that direction. Well, let's ask what these are. If this angle is theta, then this angle is theta, and this angle is theta as well. So the vertical component of the normal force is the normal force cosine of the angle theta, the angle of inclination, and the horizontal component is equal to the normal force sine that same angle. Using that and treating the vertical and horizontal dimensions separately, we can solve problems. Here's an example. Find the banking angle so that a car can make a turn of radius r with no help from friction. Well, in the vertical dimension, in this case, we would have the vertical component of our normal force, which we just said was Fn cos the angle of inclination, and that's got to be equal to the weight if the car is not going to be accelerating either upwards or downwards. And in the horizontal dimension, we've got the horizontal component of the normal force, which we found above was Fn sine theta, and that's got to be equal to our centripetal force, mv squared over r. Well, there's a similarity here that points to combining these two by dividing. If I take Fn sine theta, the left side of this equation, and divide it by the left side of this equation, by Fn cos theta, then I need to do the same thing here, divide the right side of this equation by the right side of the left equation. The normal force cancels out, and sine theta over cosine theta is equal to tan theta, and I get tan theta is equal to v squared over gr, or solving for theta, I get theta is equal to tan inverse of v squared over gr. So that's an example of a way that we could use this to solve problems. Now we could plug numbers in. For example, find the smallest radius turn a car could negotiate without friction at a speed of 100 kilometers an hour if the banking angle is 10 degrees. So I'm being given the angle here, and I'm being asked to solve for r. So rearranging the above equation a couple steps back, I get r is equal to v squared over g tan theta. And then I just plug my numbers in. I'm going to cheat a little bit and put a decimal there and make this 10.0 degrees, so I have 3 significant figures, so I can have that for my answer. Actually, first we need to convert this to meters per second, so dividing by 3.6 gives us 27.7 repeat meters per second, so now we're in SI units. So I plug that into the numerator, square it, divide by 9.81 meters per second squared, multiplied by tan of 10 degrees. And I get r is equal to 446 meters. So that's the smallest radius turn that the car could negotiate. If we back up for a moment, notice that here in the horizontal dimension, the only force acting was the horizontal component of the normal force. If there was friction operating, if the car was actually trying to slide up the hill, then friction would be pushing it back down the hill. The force of friction would be opposing the motion, and that could form part of the centripetal force. If you're wondering why friction would be pointing down the hill, imagine this is my track, and the bike does not have enough centripetal force just from the normal force to pull it in towards the center. It's going to try and go off in a straight line, as Newton's first law says it would. And if you can see from here, this is our top view, that would mean it was actually trying to move up the hill. The force of friction then would oppose that motion. So that's an introduction to some applications of centripetal motion.